Okay, so we're going to talk about the second law of thermodynamics. Okay, the zeroth, oh well, no, so the zeroth law says if two objects are in thermal contact and if there is no net exchange of heat, heat is being exchanged but no net exchange of heat, then the temperatures are the same. The first law of thermodynamics states it's an energy of conservation principle, and it just states this, okay? So if a system absorbed heat and then it did this much work, so this is your earnings and this is your spendings, this minus that gives you the increase in your bank balance, okay? So it's just a conservation of energy principle. The second law of thermodynamics, okay. All right, so, I mean, this didn't happen in this order, but let's say, okay, so let's say it happened in order. Okay, so you have the zeroth law of thermodynamics, you have the first law of thermodynamics. Why did you need a second law of thermodynamics? Okay, so you need more and more laws if there are phenomena that these guys cannot explain. Then you observe a new phenomenon that cannot be explained by these guys, so then you need this guy. And then if there's another phenomena that you cannot be explained by these guys, then you need another law. Okay, so that's how subjects develop. Okay, so let's see what cannot be explained by these guys. Okay, so I'll give you an example. So this is just conservation of energy principle. Okay? So here's an example. We'll look at this example. So here's this room. We have a glass of so this room is at 20 degrees Celsius. We'll pour a glass of hot water at 100 degrees Celsius. What will happen? What will happen?
The water will lose energy.
Heat will flow from here to there, okay? And let's say the entire thing will come to 22 degrees Celsius, 22 degrees Celsius. Okay? So what happened? Heat flowed from here to there. Okay? All right, let's say 1,000 joules of heat flowed from here to there. Yeah. Now let me do the following. Let me make heat, I'll take the heat from the room and put it back there. 1,000 joules back. Do you ever see this system going from here to there? Did you guys understand that?
No, oh wait.
So what I'm going to do is, so eventually it came to equilibrium. Now I'm going to ask that 1,000 joules move from here to there. I'm just going to order it. Do you ever observe this in nature? You don't observe this in nature. But, energy was conserved. All I asked is move energy of 1,000 joules from here to there. All that happened in this process was 1,000 joules moved from here to there. I'm just moving it back. That's not violating energy conservation. But you never observe this. Okay? This is perfectly fine with the first law. It's not violating the first law. But, this never happens in nature, and so you need a new law to explain why this never happens. Yeah? And the second law introduces a quantity called entropy. And entropy, so what the second law says, in all processes, entropy, either change in entropy is always greater than or equal to 0. Okay? So when this glass of water cooled down, entropy increased. Okay? And you do not observe this process in nature because in this process, entropy would decrease. Okay? So that's the second law. Okay. Well, this is like saying, so all you said was, okay, you introduced something called entropy. Well, there's more to it. But right now, it's like saying, I live next to my neighbor. That's not saying a whole lot. Okay, all we said was there's entropy, and in some processes that you observe, entropy increases. All right, so eventually we'll tell you at the end of the chapter. Okay, what happens is, okay, when this cools down and this goes there, what happens is the number of microstates increases. Okay, so the number of microstates with an even temperature is much higher than that. And entropy is measured by, what is this guy? That's the Boltzmann's constant, and log W. This is the number of microstates. All right, so what the statement is saying is the following. So now you have a little more meat on that bone. Okay, for this state, let's say this is the number of microstates. W1 is the microstates, and I'll come to that statement in a second. W1 is the microstates with the room being at 20 degrees Celsius and the glass of water being at 100 degrees Celsius. Okay? W2 is the number of microstates for the room being at 22 degrees Celsius and the water being at 22 degrees. It turns out that W2 is much, much larger than W1. Okay? So it turns out that entropy in this state is much higher, and so the system runs from here to there. Yep.
So entropy is kind of proportional to like the size of.
So it's proportional to sort of the number of microstates.
Micro.
Well, now let's ask, what is a microstate?
Yeah.
Okay, that's the next obvious question. All right, let's say I have $100. I give Jalen $10, $5, $5, and the rest of you guys $1. Or I could give $20, $0, $0, $1 to everyone. That's a microstate. Each distribution is a microstate. Did you guys understand that?
So each distribution of particles is a microstate.
Each way of distributing the energy. That's simplistically saying that. Okay. So how much energy does this room have? I don't know, 10,000 joules. How many particles are there? Oh, you gotta back it up with a number. A lot is,
I don't know, 6 moles.
100 moles, 1,000 moles, 10,000 moles roughly. Okay, 10 to the power of 28 molecules. Now you guys understand. To distribute energy to all these particles, there's so many ways you can do that. Okay? So obviously this is very hard to calculate, the number of microstates. Okay? But that's in principle a formula. Okay? So in nature, all processes happen such that the number of microstates of the system and the surrounding that it is interacting with increase. All processes happen such that entropy is increasing. Okay? Only processes occur in directions where entropy is increasing. Okay? That's the idea. Did you guys understand that? All right. Any questions on that? Okay. It takes a while to sink in. Okay. Entropy measures disorder. So all systems tend towards higher disorder. See, if you knew this as a kid, you could use this against your parents, when they ask you to clean up your room. You say that's the natural order of things, All right. All right, so the first law of thermodynamics does not preclude this process from happening. That is, heat flowing from the room to there and getting the cup back hot. First law of thermodynamics was a conservation of energy principle, and energy principle was conserved when you moved heat from a colder to a hotter region. But you never observe that in nature, okay? And now you can state that. Why do you never observe that in nature?
Because it doesn't follow the second law of thermodynamics.
Because entropy would decrease, okay? So if that happened, if heat flowed from a colder place to a hotter place, entropy would decrease, okay? On its own. Okay. All right, so that's why you needed the second law of thermodynamics. There are processes that occur only in one direction and not the other direction, even though energy would be conserved in both directions. Okay? And so second law of thermodynamics expresses the existence of a quantity called entropy of a system and states that entropy of an isolated macroscopic system never decreases. Okay? So only processes where entropy stays the same or increases can occur in nature. Okay? And then we'll come to that later. All right. So here's another example. Heat flowed from here to there, and this system evolved to that. Now you'll never observe in nature where heat flows from here to there and the system goes back to that. Okay? All right, in this process, entropy increased. In this process, change in entropy would be less than 0, and so you never observe this. Okay? All right. If this process could occur this way and that way, that would be a reversible process. Okay? For reversible processes, change in entropy is 0. And you can have them go both ways. For irreversible processes, you can't go backwards. Okay? All real-life thermodynamic processes are irreversible. Okay? So all naturally occurring processes, entropy increases. Okay. So a reversible process is one in which the system and the environment can be returned to their initial conditions. Okay. So again, the universe can be returned to its original condition. Okay. So, for instance, let's go back to this example. Okay. What happened here? Heat flowed from here to there, and you went to this state. You can't have heat flow back to here to there, and get the hot cup again. Okay. If you did that, what you would find is you would end up. You can use a refrigerator, draw heat from there, and put it in there. But what you'll find is you would end up with the room being hotter, not at 20 degrees Celsius. Okay. So you cannot return the system and the universe back to its original state. Okay. So all naturally occurring processes are known to be irreversible. Okay. So now here are the properties of entropy. Okay. So entropy is denoted by S. It measures disorder in a system. Okay. Now, we can calculate change in entropy in terms of the heat gained or lost. So this is what most engineers used, and this is the practical way to. It's very hard to calculate entropy itself. Hard to calculate for any system. Okay. Now, change in entropy can be found. Change in entropy is heat absorbed by a system divided by the temperature at which it absorbs the heat. Okay, and that's in Kelvin scale, so that will be joules. This is what's used in practice. Okay, now if you wanted to calculate entropy, the entropy, so for instance, if you wanted to calculate the entropy of this gas in this room, of the gas in this room, the entropy would be K times log W. What is W?
Microstates.
Very good. Number of microstates for this. Okay, number of microstates. Okay, so what does that mean? How have you distributed the energy among the 10 to the power of 28 molecules? And that's very hard to calculate. Okay, so and for most systems this would be very hard to calculate, and this is a very hard problem to do. So in practice we use this to calculate the change in entropy. Okay, now change in entropy, we don't know the original entropy. All we're doing is how much the entropy increased by. Okay. Now just to show you, so this formula, so watch this. So this is Mr. Boltzmann's tombstone, and he was a pretty smart dude. That's after whom that constant is named. And that's what he was most proud of. He did many things. That's the formula he came up with. S equal to K log W. Okay? So like I said, he's, I would say he's an Einstein caliber person. All right? And that's what he's proud of.
When did he die?
I think in the 1800s. Yeah. Okay, so we're learning about entropy. It measures disorder. Absolute entropy is hard to calculate. It's a state function. What does that mean? Like energy, pressure, temperature, it just depends on the state of the gas. Okay, so it's a state function. So entropy is a measure of disorder. It's a state function. Change in entropy during a process depends on only the initial and final condition. Okay, so if you're dealing with gases, PV diagram, and this was initial state, this was final state. Okay, this is the final entropy, initial entropy. It doesn't matter how you get from here to there, change in entropy is path independent. Okay? Just like change in temperature, change in pressure, change in internal energy, they're all path independent. Okay? Entropy of a system can be calculated one of two ways. So it can be calculated. So this is the practical way to calculate. All you do is you take little steps from going in from here to there. Take little step in going from here to there. Each little step, that's how much heat you absorb at that temperature, and just add them up. And that's an integral, okay? So you guys, that's what calculus teaches you. So each little step, the change in entropy was dq by T, and sum it all over from initial to final state. And that's the change in entropy. Okay? All right. So this formula, what it's saying, the entropy of a system, if you wanted to calculate the entropy for a given state, is the natural logarithm of the number of different ways its total energy can be divided amongst all its constituents. Okay, this is a loosely accurate statement. The number of fully specifiable accessible microstates. So W is the number of microstates of the system. Okay. All right. So what we're saying is the macro state of this gas is, what is the macro state? The temperature in this room is 20 degrees Celsius. The pressure is 1 atmosphere. The volume is about 1,000 meter cube, and so on. For this, you can calculate the number of microstates. Now, if you change the temperature, the number of microstates changes, okay, and so on. Did you guys understand that? Okay. If you understood this, this is good. This is the hardest chapter to understand in this course. Okay. And people find this is the hardest part to understand in thermodynamics, I guess. Entropy is a measure of how much energy is not available to do work. So here's an important statement. What does that mean? Okay, so if you have potential energy, 100% of that can be converted to work. So for instance, in a dam, there's water behind a dam, you store potential energy, you can convert all of that to electricity and work and so on. You have kinetic energy, you can convert 100% of that to work. You can convert all of that to lifting something. You have heat. That's what your car does. What does your car do? Yeah, you burn gasoline, you produce heat, and then now you want to convert that to work. Okay? You converted 20% of that to work. What happened to the other 80%? You couldn't convert that to work. You would have loved to do that. You were rich and you just threw it out the window. Yeah. So that's what entropy is about. Okay? So entropy is a measure of how much energy is not available to do work. Okay? That unavailable energy is of interest in thermodynamics because the field of thermodynamics arose from efforts to convert heat to work. You know, the steam engine and all that. All right, so again, this was the amount, infinitesimal change in entropy. You would absorb this much heat at that temperature. What are the units for that temperature? Kelvin. Okay, so this temperature is always in Kelvin. What are the units for heat? Joules. Joules per Kelvin. So entropy, the units for entropy are joules per Kelvin. Okay, that's our unit. Okay, so this is the infinitesimal change, and you sum over all the small changes, you get the change in entropy. Now, you are often interested in calculating the change in entropy. Okay, let's say this was the initial state of your system. There is the final state of your system. Okay, now change in entropy doesn't depend on the path you took, right? Change in entropy. Entropy is a state function, so there is the value of the entropy at the initial final state. Change in entropy as S final minus S initial. Doesn't matter what path you took. But you want to evaluate that, so you want to evaluate this integral. So what do? You be smart about it. Evaluate that integral along a path that you can easily calculate. And change in entropy is the same along every other path. This is hard to do, this is easy to do. What path will you choose? Easy path. The system might have gone along that hard path, but you don't care. Yeah? You use this path to calculate the entropy. Okay? And that's the idea. You guys understand?
Yes, sir.
All right. Okay. So temperature, pressure, and volume of a gas fluctuate unpredictably during an irreversible process. Okay. You won't worry about that. However, since entropy is a state function, the integral below can be evaluated along a reversible path. Even though reversible paths are idealization, you just use those to calculate change in entropy. Okay. Now, we'll show you a calculation. I won't go into the details. This is an example that's used in all your thermodynamics classes, so we'll talk about this. A free expansion, what this means is, okay, you'll take a gas in a chamber, and you'll have a perfect vacuum there. Now, that's impossible, but this is a thought experiment. This is idealization. And then what we'll do is we'll open the valve and the gas will expand. Okay, what is the idea behind this? An expanding gas does work, right? When does it do work? When it has to push against something. But if this was a perfect vacuum, it doesn't have to push against anything. So that's why we took this idealization. So this gas is expanded, it's not done any work. Since it has not done any work, work is when you spend energy. If you haven't done work, you haven't spent any energy, so your temperature hasn't dropped. So this would be a free isothermal expansion. Okay. So it has expanded. Okay, so that would be a free expansion. Now, you can nitpick. So as this thing is filling, now you are having to push, but we won't get into that. Okay, so we're just going to say. Okay. So for a free expansion, so using that ideal process, you can do this integral. So in the free expansion, change in internal energy is 0. dq is the work done, dq equal to dw. The heat absorbed is equal to dw, which is p dv. And so you can calculate that. So in this free expansion, in this process, okay, when the temperature remains constant, for an ideal gas, here's a formula for the change in entropy. Okay, in a very special case. So this is for an isothermal process. We're just giving you a formula, okay? So now entropy change for an ideal gas for a more general process. So this is the entropy change for an ideal gas when the temperature changes and the volume changes. Okay? So here's a formula. This is for an ideal gas. Have I given you a formula for entropy change when you heat a solid or a liquid? No. Okay. But that would be easy to calculate because heat absorbed for a solid and liquid is easy to do. Okay. So for instance, for a solid and liquid, take the mass of the liquid or solid, specific heat times the change in temperature divided by that. And if the specific heat is constant over the range, change in entropy is mc log T final minus T initial. Okay? So for solids and liquid, it's easy. All right, so you have a formula for the change in entropy. So the second law of thermodynamics states that for all processes, okay, if a process occurs, that means the entropy has either increased, change in entropy is either greater than 0 or 0. When is it change in entropy 0?
When it's a reversible process.
Okay, it's a reversible process. Irreversible process. Okay. What are all processes in nature? Irreversible. Okay. No. Okay, so there were processes in nature that occurred only in one direction. Heat flowed from hot to cold. Heat never flowed from cold to hot. Okay, first law was okay with both processes. The second law is okay with this process. Second law is not okay with this process. Okay, so that's what you learn. Okay. Okay. Again, so I mean, this is a very simple statement. When do you need a new law? When the existing laws cannot explain all the phenomena. That's when you need new laws. Okay. When do you stop needing new laws? When everything has been explained. Then you don't need any more new laws. Okay? All right. So now we'll get to practical things. We'll get to heat engines. What do these fellows do? What they do is they absorb heat, do some of it, convert some of that to work. What you'd kill to do is convert all of that to work, but the laws of physics don't allow you to do that. And then you dump the rest of it. Okay. You burn gasoline in your car, that heat is converted to the motion of the car. 20% of that is converted to the motion of the car, the rest is dumped out. Okay? Dumped into the atmosphere. Okay. In the US, these are rough numbers because, I mean, the world is doing the same. 80% of our energy comes from fossil fuels. What are fossil fuels?
Oil, natural gas.
And coal. Okay. All fossil fuels, how do you get the energy from them? You burn them. Okay? You burn them, convert some of that to motion, electricity, this, that, and the other. The rest you dump. We spend about $1 trillion on energy. $700 billion is thrown out. Did you hear that?
Is that worldwide or just US?
That's the US.
So are we still trying to make it more efficient, or did we just give up?
Or is it not possible?
It's not possible. That's heat engines. Okay, enjoy your lunch today. So, if you were getting all your energy from electricity, a Tesla converts almost 90% of the battery energy into motion of the car. Okay, so the idea would be to get electricity from solar cells and wind, okay? And then you would be much more efficient. Okay. All right, so our life depends on heat engines right now. Okay, so you get heat from a source, convert some of that to work, and then dump. Okay, so now we've been using heat engines for 200 years now. We've had this question, burning question, what is the best we can do? Okay, and Mr. Carnot answered that question. He was a French engineer. Okay. So what he did was he considered an ideal heat engine. Okay. Ideal heat engine didn't have any friction and stuff like that. It worked on reversible processes. And of course, reversible processes are not possible, but that's what he did. And so what he did was he established an upper limit for the efficiency. This is the best you can do. That's what he said. Okay? So he gave us a formula for the maximum efficiency possible. Of course, all real engines have an efficiency less than that. but at least you know what is your upper limit. That's the point. Okay? All right, so that's what we're headed, where we're headed. Okay? So heat engines are devices that convert thermal energy to mechanical energy. All heat engines have a working substance which goes through a cycle. Remember, we did work done during a cycle and all that. In an automobile engine, the working substance is a gasoline-air mixture. Here's a simulation of a gasoline engine. Do you guys want to see that?
So is E-Max 20%?
No, Emax for your car is 70%.
So we just suck.
Yeah, you just suck.
I'll make it better.
How about a hydrogen cell?
Hmm?
Have you heard of the hydrogen cell cars?
Yeah, fuel cell cars.
Yeah. What are the efficiency rates on those?
Fuel cells can be 80% efficient. Mhm.
This is what we need to work on.
Is that the,
Yeah.
that's a little bit.
Then we'll be.
Well, the Japanese are betting on that.
That's good. That's all they do.
What's that?
That's all they do. Make anime. So it's-
That's not working. All right. It worked on my computer. And I can't do this link. It's not.
It's not linking.
Yep. I don't know why this PDF on the iPad doesn't work. All right. So heat engines, again, heat engines, you have a source of heat. So this is the hot reservoir. So this would be the temperature inside the cylinder in your cars, for instance. You're absorbing heat from there, converting some of that to work, and dumping the unusable heat into the environment. Okay, so that would be the heat sink, and that's the atmosphere in your case. Okay. The efficiency of a heat engine, the efficiency of any heat engine, how much work did you get out of absorbing this much heat? So again, like we say, when you absorb about 100 joules of heat in your car, you got 20 joules of work out. Okay? So that's your efficiency. Okay. So Mr. Carnot, a French engineer, showed that a theoretical heat engine in which all processes are reversible. So this is an ideal engine, there's zero friction and all that. For such an engine, he calculated the efficiency, and all real engines are less efficient than that. So he just established an upper limit. Okay? All real engines are less efficient than Carnot engines. So a Carnot engine establishes an upper limit. Okay. Now this is just an energy conservation principle. You absorb this much heat, you did that much work, and so you had to dump out the rest. Okay? So QH is the heat absorbed, QC is the heat dumped. The subscripts are H is the hot reservoir, C is the cold reservoir where you're dumping heat. Yeah. So the efficiency is of a heat engine is work done divided by that, and so that's equal to that. This is true for all heat engines. What Mr. Carnot showed was, for a Carnot engine, this is equal to TC by TH. That's what Mr. Carnot showed. That is, this is the temperature of the cold reservoir, and that's the temperature of the hot reservoir. And look at this is very powerful. The efficiency of an ideal engine just depends on the temperature between which it's operating. There's nothing about how it was built or anything. Okay, so that's the genius of this.
So we should run all our energy plants in Arizona.
Okay, so here's the efficiency. Okay, what would you like for the efficiency to be? 1. Convert all of the heat to that. How can that be 1? Either the cold temperature, this is in the Kelvin scale, so this has to be absolute 0, and that can be 1. Or this can be infinite, and that can be room temperature if you want. If this is infinite, so inside your cylinder, if the temperature is infinite, then your efficiency is 1.
Wow.
Okay?
Canada.
Alaska, yeah. Okay, so you take a car from Florida to Alaska, you would increase efficiency. Yeah. Okay. So again, Mr. Carnot used an ideal engine to establish an upper limit. And in his engine, you had 2 isothermal processes and 2 adiabatic processes. In an adiabatic process, you're not absorbing heat, you're absorbing heat during this expansion, and you're dumping heat during this compression. Okay? And change in entropy is you change in entropy when you absorbed heat, and entropy decreased when you dumped heat. Okay? But for an ideal process, so he used reversible processes, so change in entropy for a reversible process is 0. And so Mr. Carnot showed that QC or QC over QH is TC over TH, okay, for an ideal heat engine. And that's where this formula came, QC. Okay. So Mr. Carnot showed that for his engine, there is the efficiency. Okay. So that's the upper limit of efficiency for an heat engine operating between those 2 temperatures. Okay, and that's why it's useful. A Carnot engine is not possible in real life, okay, but it's a theoretical concept that establishes an upper limit. So if your car engine were a Carnot engine, it would be 70% efficient. It's actually 25% efficient. Okay. Plenty of people have tried to do improvements. Obviously, it's very hard to do. Okay. It's a little higher efficiency, but we have to, you waste a lot of your energy on the foo-foo stuff, air conditioning, this, that, and the other. Okay. All right, what we'll do is we'll talk about refrigerators, and then we'll stop, and then I'll do some of the fun stuff next lecture, and on Wednesday we'll do that and the problems. Okay. All right, so we'll just talk about refrigerators. What do refrigerators do? I'm sorry?
Cool food.
Cool.
Keep food cool.
Yeah. So here's a refrigerator. You go buy a drink that is warm, put it in the refrigerator.
Heat transfers too.
I'm sorry?
Heat transfers out of the.
Yeah, so it removes, so inside the refrigerator it's 4 degrees Celsius, and outside in your kitchen it's 20 degrees Celsius, and it removes heat from the colder region and dumps it in a hotter region. Nature wouldn't do that. So what do you have to do this? You have to do work to do this. You have to spend money to do that. Okay? So a refrigerator is a heat engine in reverse. It's absorbing heat from a colder region. You're doing work and you're dumping it into a warmer region. Okay. So a refrigerator will work as long as it's plugged in. The instant you unplug this will stop. Okay. Now, do you guys understand that? Okay. All right, so you have to do work to remove heat from a colder region to dump it in a hotter region. Okay. Now, let's see how in practice it's done. Okay. So we'll take you back to latent heat. Okay, so we'll make sure you understand this. You guys know so here, let's say here's 1 gram of water, and I want to convert it to steam. What happens? How do I convert it into steam?
Increase the temperature.
I'm sorry?
Increase the temperature, add energy.
So this is at 100 degrees Celsius, that's on 100 degrees Celsius. So you have to add heat, and you have to add 540 calories. So during this phase change, the temperature did not change, and this is called the latent heat of vaporization. Okay, so when this phase change happened from liquid to gas, heat was absorbed. Okay. Now here's the deal. Okay. So let's say you have water. We won't boil it. What we'll do is we'll hook it up to a vacuum pump, and the vacuum pump sucks air, and what it does is, and then it'll enhance the evaporation. And every time 1 gram of water evaporates, it takes away 540 calories of heat. What happened to the rest of the water? Heat is being taken away, so the rest of the water is cooling. Did you guys understand that? What happens when we take this water, send it to the compressor, and turn it back into water? What will happen? When you take the steam or the gas back and turn it into liquid again, it will release the 540 calories. Did you guys understand that? Everybody understand that? When you convert liquid to gas, it absorbs this much heat. Okay? And when you convert gas to liquid, it gives back that much heat. All right? If you understood that, now here's a pipe. This is inside the refrigerator. We're taking water, hooking it up to a vacuum pump, and vaporizing the water. This is inside the refrigerator. Every time 1 gram of water vaporizes, it absorbs 540 calories of heat from the refrigerator. Take that water outside, put it through the compressor. The water vapor is turned back to liquid, and it dumps out the heat. Except that you're not using water, you're using Freon or some coolant. Okay, how do you decide what it is that you're using? Okay, so if you want to, inside the refrigerator, if you want to maintain a temperature, so inside a freezer, for instance, I don't know, inside the freezer you're maintaining -5 degrees Celsius. What you want is a liquid that evaporates, whose boiling point is less than 5 degrees Celsius. Okay? Okay, so that's how you decide what coolant you want. Okay. All right, so again, you guys understand that inside, wherever you want to cool, you vaporize a liquid. It absorbs heat when it vaporizes. Bring that liquid outside. You turn the vapors back to liquid, and it'll dump out the heat, and then you just dump it out in the kitchen. Where was the work done? In the vacuum pump, sucking on that to vaporize it. And in the compressor, turning the gas back to liquid. Okay, so that's where the work is done. So that's how you remove heat from a colder region and dump it out in a warmer region. Okay? All right. So the coolant is vaporized in the evaporator inside the refrigerator. The vaporizing coolant extracts heat from the refrigerator. It is then compressed and sent through this condenser where it exhausts heat to the outside. Okay. So liquid to gas, this is when you absorb heat. Gas to liquid, that's when you dump out the heat. You're absorbing heat from the inside, you're dumping heat on the outside. Yeah. Did you guys understand that? All right. Air conditioners and refrigerators are heat pumps. What does a water pump do?
Pumps water.
Water from a lower level to a higher level. Water wants to flow from a higher level to a lower level. Water pump pumps water from a lower heat pumps heat from a colder region to a hotter region. Okay. All right. We are always after efficiency. Okay, you want the best bang for your buck. Okay. So, again, here's a following Carnot. Here's an ideal refrigerator. This establishes an upper limit for the efficiency of a refrigerator. Okay, and that is coefficient of performance. Okay, so what we want, how much heat did you remove from the inside of the refrigerator, and how much work did you have to do that. Yep. All right, so here's the ideal COP just depending on the temperature. Typical COP for household refrigerators is about 5. What does that mean? To remove 5 joules of heat, you have to do 1 joule of work. And then you're dumping out 6 joules in the kitchen. Okay. So your refrigerator is getting colder, the kitchen is getting warmer. Okay. See, the entropy of the universe increased. You removed 5 joules of heat here and you dumped 6 joules there. You just didn't move heat from a colder region to a warmer region for free. You removed 5 joules of heat from a colder region, but you had to dump 6 joules into a warmer region. Yeah. All right, guys.